Okay, it's my pleasure to present some results from the DIGIT key project with Herschel. And I'm speaking on behalf of the DIGIT team, more or less listed here, but the results I'll talk about today are led by the people indicated in red. So DIGIT is a project which involves the change in chemical state from the embedded phase through the disk phase. So we're looking more at microscopic changes primarily. So we're looking at spectral features of the dust, ice, and gas. We cover a range of masses and luminosities. We primarily are going to talk about PAX spectroscopy, though we have some hi-fi spectroscopy and PAX photometry, which I'm going to talk about first, actually. So first I'll show you the sample. These are the embedded objects over here, so not so much of interest to this talk. The disk sample is over here. The black dots are Herbig AEBE stars. The red squares are T-Tauri stars, and the blue triangles are weak-line T-Tauri stars. And it's the weak-line T-Tauri stars that I'll talk about first because we have the photometry on those. The overall disk sample involved full SED range PAX spectroscopy. So we have a complete spectrum for about 20 objects, mostly Herbig AEBs because they're brighter. We have scans of the Forsterite region for a smaller number of objects. But I'm going to talk about first the results on the photometry of weak-line T-Tauri stars. And the game here was to follow up issues of whether weak-line T-Tauri stars, which tend to have very little evidence of disks in the mid-infrared, would show up more evidence of the far-infrared. And we're probing issues like this. I don't need to go through this slide. We all know that grain growth, grain settling, migration, photoevaporation, clearing by planets, all these things are at play. And so we're asking about what is the overall evolution of the SED in this first part of the talk. So the basic result is for the weak-line T-Tauri stars in our survey, we generally confirm the picture that if you are in this sector, which is more or less the classical T-Tauri stars based on the H-alpha velocity width, which is kind of cut off there, you have primordial disks. If you're over here, less than some characteristic H-alpha velocity, you either have no disk, as indicated by the red, and we see no excess whatsoever in those, or an excess which is characteristic of a debris disk rather than a primordial disk, and those are indicated in green. Now, there are some interesting ones. There are two cold debris disks seen only at 70 microns, and one very interesting primordial disk. This is T-Cha. It's a weak-line T-Tauri star with a massive outer disk. It's one of these transition disks with a wide gap, a planet candidate detected within the gap. And this shows you some resolved submillimeter resolution, but what we added was the SED. As Catherine explained, we now fill in this part of the SED, and in our case, those points lay below the previous models. So there has to be less dust than previous models suggested. And what that means is that the outer, the disk here is very small. That is, it either is truncated fairly rapidly beyond the inner edge, or it has a very steep density gradient. So it doesn't continue out very far. And so Cieza et al. Argued that this is a good match for models in which you are in the phase of runaway accretion, gas accretion on a giant planet. That would explain the high luminosity of the possible planet candidate. And hydrodynamic models by Dodson, Robinson, and Salek suggest that you might need multiple giant planets to produce these sharp edges in this outer ring. Okay, so let me move on to the other part of dust, which is on the microscopic scale. We're looking at what is the features of the dust, what's the mineralogy. And the characteristic feature that is of value to us is the 69 micron Forsterite feature, which is shown here in kind of the best example. We see this in 7 Herbig AEB stars and 1 T-Tauri star. Now, this feature is very nicely diagnostic because its central wavelength depends very strongly on its iron content. Here's laboratory data showing how the peak wavelength shifts as you increase the iron content. It depends quite a bit more weakly on the temperature of the grains, shown here. You can see that shift is quite a bit smaller. And the shape, the width, depends on the size of the grain. So it's quite diagnostic. And so Bernhard Sturm has made large grids of models and asked to minimize chi-squared. So these are the chi-squared minimum surfaces, with blue being good. This is iron percent on this axis, and most of them you can see are constrained to have less than 1% or so iron, but a range of temperatures. There's one exception. ABO Riga seems to have a higher amount of iron, so something like 3 to 4% iron content in the forsterite. Now, one of these objects, HD100546, about which we've heard some earlier, and you'll hear some more, was modeled in detail by Heiss Mulders with a 2D radiative transport code. You can see the model over there. It has this inner wall of the outer disk at 13 to 20, about 13 AU, and the forsterite seems to come from very close to that wall. In that region, the crystalline mass fraction is high, and the iron content is very low. So here's his model showing the location of the forsterite feature that we see. Okay, so the I in DIGIT stands for ice, and until recently I couldn't say anything about ice. Catherine already introduced this ice feature that is around 60 to 70 microns. It's broad and weak, and we had to wait until we had really very good calibration of the spectral response before we believed it. We now believe it in a few disks. Catherine mentioned McClure et al. Seeing it in GQ loop. And so I'll show you those results. We do confirm that this was seen with ISO. We do not confirm hydrous silicates as claimed from ISO spectra. So this is the ISO data on this particular object. And you can see this peak here, which is crystalline ice, and then sort of a very broad bump around 100 microns, which is attributed to hydrous silicates. So the black data is our data, and we confirm the water-ice band now quite clearly in this source, but we don't really see an excess in the 100 micron regions. There's, of course, an issue where there's two modules that miss exactly at 100 microns, and the alignment is always imperfect, but you can see we don't see any real evidence for a feature like that. This is, again, HD100546. And you can see now, in this case, very clear evidence of a broad water feature, but really no evidence of a bump out here at 100 microns. You can also see now we have this power of the spectra, including the Spitzer IRS and the PAX and the SPIRE. We have incredible spectra over a very wide range. So now let's look at the gas. Actually, if I zip back for a second, these peaks here that you can see are representing the gas. So what's the use of Herschel in terms of measuring gas? Essentially, we're probing a different part of the disk than we will probe with ALMA, or that has been probed in the mid-infrared and near-infrared. So essentially, Herschel is looking at this region of the disk, primarily not the midplane, but somewhat below the top layers. So these are the gas detections. I'll just list them there for a second and make a few points about them. The most common thing we see is oxygen 1. We do see OH in a fair number of the Herbig A, B stars. The T Tauri stars, we see a larger fraction of these things, but the T Tauri stars were selected to be interesting, so you can't quite take that as a fair comparison. The carbon-2 line is seen fairly often, but it's usually diffuse, and so when we talk about these numbers refer to the ones that we are at least point-like, or at least we've subtracted off the surrounding emission. So at least plausibly it's associated with the star itself. CO is seen in only a few Herbig A, B stars, again a fair fraction of T Tauri stars, and we do see water in a few Herbig A, B stars, and CH plus also. This is all written up in two papers which are in the review process, Fedeli et al. And Mayes et al. So hopefully they'll be coming out in the next 6 months or so. Okay, so here's an example of the gas lines we see, again in our favorite source here. You can see CO lines, you can see OH lines, and you can see water lines in this case. Water lines are very difficult to see, and we'll show you that we have to use a trick to see them usually. Analysis of the O1 excitation along with the C2, and when we believe that it's associated. with PDR models gives you densities of about 10 to the 5th per cubic centimeter and G naughts 10 to the 3rd to 10 to the 7th. Because the C2 may still be contaminated, these are kind of lower limits, but this is the grid and the solutions on that grid. This is from the paper by Fedeli. OH excitation, similar kind of story, minimize chi-squared. You see a region, this is the red points are the data and the blue points are the model. And the temperature, rotational temperature of OH ranges from 100 to 400 K. Now, water is very challenging, so we use the fact that we have full SED scans. So there's about 30 water lines in there. Based on our observations of embedded sources, we know where the water lines are. And so we simply stack all the water lines in our spectra. And so we cannot say we detect individual water lines, but we have a signature of the water molecule. So that's what these are. And to test whether these are real or not, we do Monte Carlo simulations of stacking 50,000 random parts of the spectra to see if you create a line like this. And so that gives you the false alarm probabilities listed up here. You can see that these are quite convincing detections of water. This one, not quite as convincing. But that's the basis way in which we can find water in these weak water lines in these Herbig AEB stars. Here's a plot, again, of our best source for the CO excitation diagram. And you can see that there's evidence of a warm component around 300 and a hotter component around 900 Kelvin in this source. Most of the objects don't have detections up here, so we can't really do this for most of the Herbigs. CO is more easily seen in the T-Tauri stars again. Interesting feature, the Herbigs are divided into two classes, the flared disks and the flat disks. And we see the CO only in the flaring disks. So the analysis of that is done by Simon Bruderer. He shows that if you have a model in which the gas temperature equals the dust temperature, you cannot reproduce these high JCO lines. This is the upper, J of the upper level of CO. You could get the lower J lines, but not the lines that we see with PACs, which are up in the 20s and 30s. So he needs a model in which the gas is hotter than the dust, and that's evidence that the gas and dust temperatures are decoupled. Says you have to be up in the atmosphere where the collisions are not so fast that they couple those two. So the gas analysis is sort of summarized here. The DG tau, we see evidence that the emission is probably from the jet, and the carbon-2 is certainly contaminated. The rest of the lines are consistent with a disk origin. The high JCO needs the high temperature and flared disks, as I said, so the gas has to be hotter than the dust. The OH can be found at lower temperatures, and it's seen also in the flat disk, so it doesn't need that superheated layer. The O1 is ubiquitous, but there's a large spread in values, and it's not a very clean correlation of strength with stellar luminosity. The OH to water ratio is higher in Herbig AEB stars than T-Tauri stars, suggesting that photodissociation from these more hotter stars is probably irrelevant. And the T-Tauri spectra are richer, but of course there was a more biased sample. So if we look at just the OH to water trends, for example, from the near infrared to the mid infrared to the far infrared, so probing different parts of the disk, you can see that the Herbigs and the T-Tauris behave a little bit differently, but not so differently. But there's clearly now from this water in the outer parts of disks and the beginnings of seeing ice features out there as well, we know that there's a water reservoir far out in the Herbig AEBE disks. So just as a sort of visual summary of the results, you can look at this and see for the T-Tauri, the flared and the flat disks, and incorporating mid-infrared data, far-infrared data, and so forth, where we think different molecules are in these different kinds of disks. So we'll look at that for a second, and then I will put up my summary and stop there.
Thank you. Got time for questions?
Hi, Neal. Thanks for the talk. What's your interpretation of the variation in iron abundance in phosphorite?
I don't think I have an interpretation of that. What you find, mean, the forsterite is the iron poor end of the sequence. And what's interesting, I think, is that the low iron content is kind of in agreement with what people find in dust particles in the solar system. So it looks like the iron is primarily not in, at least in this form of the crystalline dust, and not in the forsterite, but I think that's probably more general than that. So it's going to be interesting to figure out what form the iron is in.
Any other questions? Yep.
When you say cold debris disks are rare, do you mean that they're rarer than they are around main sequence stars, so that the debris disks that we do see have to come from non-weak line T-Tauri stars? Or?
So what I said was in our sample of 30 weak line T-Tauri stars, we saw 2 cold debris disks. So I think that's the statement I would make.
Above what level, though?
I don't know what you mean by rare exactly. So this was an attempt to see if there were a lot of them, if there was a high fraction of those that don't show up at shorter wavelengths, and we didn't see a high fraction, but we did see some. 2 out of 30.
Do you expect that this decoupling between gas and dust temperature is something that you only see in this one object, 100546? Or,
No,
do you think it's more general?
That was a model for that particular source, but in the fairly small number of Herbig AEB stars where we see the CO, they're all flaring disks. So we don't see it at all in the flat disk. And so that's all consistent with the same kind of picture, that you have to be in this upper layer where the gas and dust get decoupled, and you've got the gas higher than the dust in order to see the emission. So I think that's probably a pretty general picture, at least for the far infrared lines. It may not be true for the longer wavelength lines.
All right, if there's no last questions, then let's thank Neal again. Thank you. Okay, and our final talk for this session is by Myra Osorio.